I just noticed that I had not set the sound to come from the headphone, so it came from the computer, so it sounds a little different, but it's quite audible, very clearly audible, so you have to just tolerate it. It sounds more airy, I don't know. Okay, so now that we have set up the potential vorticity substance as a diagnostic to look at this cross-latitudinal flux, and looked at the observations that show that the cross-latitudinal transport back and forth across the whole band would be close to zero. This is what leads to what is called an impermeability theorem. We start with the full hydrostatic equations in isentropic coordinates, so no restricting assumptions as such, and that's how the equation looks. We are not deriving it, but you have the time derivative of the potential vorticity, the advection term in the isentropic coordinate, and the divergence term, which depends on the thermodynamic term or the diabatic heating. This vector is essentially normal to an isentropic surface. The divergence term here of this advection term and a dissipation term. Okay, so when you have Rossby waves breaking into filaments and so on, there is dissipation of potential vorticity, and obviously there is a source of potential vorticity when you have diabatic heating. So this is a full equation, and there is the mass equation that we wrote before in terms of the potential vorticity, the isentropic mass density. So d sigma dt plus divergence of the advection term, and the vertical term is written in terms of the heating. Basically, you know that the heating is going to create, you can think of it as a mass source. If you are looking at the upper isentrope, diabatic heating below it is going to create vertical ascent and injection of mass into the isentrope. That's kind of what this is saying. In a convection, it's just the vertical advection term. Okay, so multiplying 11.6a by sigma and using 11.6b, you can derive after some algebra which we are not going through, you get this nice PVS equation, del sigma q dt plus divergence of jt, which is now the total flux, which has other terms in addition to the latitudinal advection that we looked at, adds up to 0. Or you can write it as dqs dt, because sigma q is our potential vorticity substance, plus divergence of jt equal to 0, the total flux of PVS, and that is combination of the advective flux, non-advective diabatic heating source term, and the dissipative sink term for potential vorticity. This is the remarkable thing about this derivation and this equation, is that the whole PVS reduces basically to say that within the isentropic layer, the time variability of the PVS is just related to the divergence on the isentrope. There is no source or sink. Even though there is heating and dissipation, it is still conserved within this isentropic layer, which is what implies that there is an impermeability, that across the isentropic interfaces there is no source or sink of PVS. It's just being advected around, and variability at any location is just given by the advective terms of the three combinations. So the advective term JA that we looked at before is sigma q v tilde. This is the isentropic velocity field. The diabatic term has the meridional advection of the heating, if you will, and the zonal advection of the heating term, and in the vertical, or its cross isentropic, is 0, as we already saw, and the dissipation of PVS potential vorticity substance, which you should get comfortable with. It is much more broad than just the PV we talked about before, which is not conservative when you include diabatic terms, right? It's conserved. We derive the potential vorticity conservation for adiabatic situation. So that's got meridional and zonal terms, and in the vertical it's 0. Okay, you can also think of it as a shallow water in terms of considering just the isentropes. Some drilling has started here, so I'm going to maybe stop this here and come back to explaining the consequences of this in a minute. Let me close the window. Okay.